The problem's primes and composites are polynomial time equivalent under Cook reductions. This is because to decide one of these problems, we can simply call an oracle for the other one and then negate the output. Also, clearly, composites reduces to factor in a polynomial time carp reduction. For this carp reduction, we can just take this input number x, for which we're asking whether it's composite or not, and transform it to the input x and x for factor. So we are asking, does x have a non-trivial factor smaller than x? If x does not have a non-trivial factor smaller than x, then x must be prime and is therefore not composite. On the other hand, if x does have a non-trivial factor smaller than x, then clearly x is composite and not prime. So this carp reduction really works. Putting this together, we get that primes is polynomial time equivalent to composites under Cook reductions, and composites reduces in polynomial time to factor in the carp sense. That also means that primes reduces to factor in polynomial time in the Cook sense. A natural question is whether the other direction is also true. So whether factor reduces to primes in polynomial time in the Cook sense. In other words, suppose we have an efficient algorithm for primes, would we then also get an efficient algorithm for factor? Because the other way around, it's true. So if we had an efficient algorithm for factor, we would have an efficient algorithm for primes. However, for this other direction, we don't know the answer. We do not know whether factor reduces to primes in a polynomial time Cook reduction. Many, if not most, computer science do not believe that this is the case, but it's not impossible. One reason why some or many people do not believe that this is true is because we know that factor is an NP intersect co-NP, but a lot of people don't believe that factor is in P, so they don't actually think that there is an efficient algorithm that can decide this language factor. The belief that factor is not in P is exploited in some cryptosystems like RSA, for example. These cryptosystems would break if we would suddenly discover that factor is in P. So at least people who are using those cryptographic schemes really hope that factor is not in P. On the other hand, the problem primes seems to be much easier. For a long time it was not known whether primes is in P or not, but since 2002 we know that primes is indeed in P. So not only is it contained in NP intersect co-NP, but actually we can decide whether a number is prime or not in polynomial time. So to summarize, factor is known to be in NP intersect co-NP, but not known to be in P. And many people actually don't believe that it's contained in P. Primes, on the other hand, is known to be in P. We have an efficient algorithm to decide whether a number is prime or not. However, the efficient algorithm for this is quite sophisticated and involved, and therefore we are not going to discuss it here.